I don't know, yeah, you're hearing me well. So hello everyone. Today I will present to you our work, which is dedicated to verify the control flow integrity and also the code execution of integrity of programs executed on RISC-V core using the trace encoder. So it will be designed to be verified against fault injection attacks. So firstly, to talk a little bit about the context. So the fault injection attacks are powerful attacks that can change the behavior of the program. And as we can see here, a small example of a microprocessor that will be executed on comparing a user pin code to a correct one that will be stored in its memory. So in the normal behavior, since these two pin codes are different, we have an access that will be denied. However, injecting a fault attack on this operation on a RISC-V core can bypass the verification by skipping or corrupting the result of this verification. In this case, even though that the two pins are different, the access will be granted. So by this small example, we can see why it's necessary to verify the program behavior of a program that is executed on a RISC-V core. The trace encoder, which is a debug model designed by the RISC-V Foundation, can give us information about this program behavior. So as we can see here, that the trace encoder will be connected to the RISC-V core, and also it will receive the executed instruction of the program. And this trace encoder will compresses at runtime the sequence of discontinuity instruction executed by the RISC-V core, and it will report it into trace packets. So developers using these packets and via an external debug tool, they can reconstitute the program flow by having also access to the binary code. So let's say that the trace encoder will send packets, and the packets that will be sent are known by the trace encoder standard. So they could be sent after fulfilling several conditions. So in the next slide, I will present to you a condition that the packet is sent after that an unpredictable discontinuity instruction has been executed. So by unpredictable, I mean that the discontinuity instructions that the target address is not known from the binary code. It could be like the return instruction. So here in this code, the assembly code shown at the address 22C, there is a return instruction that is executed, which is trace encoder will send a packet after reporting the destination address, which in this case is equal to 374, which is the address of the next valid instruction that is executed after the return one. If you continue as another example, so at the address also 390, there is another return instruction executed. In this case, in addition to the destination address that will be reported, there is an instruction at the address 380, which is a branch instruction that is executed. So the trace encoder will compress and will also send information about this branch condition, which in this case will say the number of branches that have been executed, in this case is equal to 1. And also it will send also the branch map, which is the branch vector to say if the branch has been taken or not. So having this information sent by the trace encoder, could we use it to check the program behavior and detect if a fault injection attack have been made on the RISC-V core? Well, the answer is yes, and this is a contribution of our work. So we use the trace encoder, but not for debug purposes, but we developed a solution based on this in order to verify the control flow integrity of the program. And so how our solution works, we can see the additional blocks, which are in green, they are the contribution and the additional blocks to this solution. So firstly, the program or the user code will be parsed via our custom program who will analyze statically this program in order to extract all discontinuity instructions with their addresses and also the addresses of the following discontinuity instructions. From this extraction, we will generate metadata that will be stored in the memory of our solution. And while executing the code via the RISC-V core, the trace encoder will send packets and telling us or giving information about the flow that is followed by the program. In this case, our solution, which is a trace verifier, will check and will verify and compare the content of this packet to the metadata that are stored in its memory in order to check if the program take a path that is validate and it's correct. So I explain a little bit more about our solution. So the trace verifier, and so here we can see the architecture, which is contained of different blocks. The FIFO2 stores the packets that are sent by the trace encoder, and also the verification processes. So how it works? So verification process will start when a packet is sent from the trace encoder, it will be stored in the FIFO, and then the finite state machine will read it in order to extract the information from this packet. And then we will navigate through our memory in order to constitute the path that is, for us, it will be the faultless path. And at the end, we will verify the integrity, so we'll compare, let's say, the destination address of the packet that is sent and also the one that is found by navigating in our metadata. So with this approach, we can detect the fault injection attacks so attacks skipping a function call. This is because the trace encoder will generate other packets that are not attended or by our trace verifier. And also we can detect changing the address of this function, and this could be able to do so by using the shadow stack in our trace verifier. So here I put an example of a backward edge attack. However, this approach has several limitations. So if you had a corruption of a discontinuity instruction, like specifically to the branch one, if you change a branch of not equal instruction to a branch of equal instruction. So in this case, the trace encoder cannot give us information related to this attack because it would only tell us if the branch has been taken or not. The other corruption is the other limitation is the corruption of a non-discontinuous instruction that does not change the flow of the program. And the third one is that with this approach, we can protect partially the program flow towards the first pipeline stage, which is the fed stage. With this approach, our work didn't stop here, so we exploit the trace encoder standard thanks to its open source in order to cover these limitations. And this is done so we enhance the trace encoder standard to cover also more false models. I will explain in the next slide how we did this. So now with the enhancement, we did modification to the trace encoder in order to send the packet after each discontinuity instruction and not only by fulfilling the conditions in the standard. And also to cover more the code integrity and the code execution integrity, we added signature model to the verification circuit, as we can see here. So if you want to check inside the trace encoder, there will be a signature model that will compute the signature of the basic block instructions if you want to verify the code integrity. Otherwise, if you want to check the control flow and execution integrity, that means that to verify that the instruction is correctly executed from the first stage till the last stage of the pipeline, there will be a signature or a signature model related to its signals. And this signature will be sent to the trace encoder, which will report also via a packet the signature to be verified by the trace verifier. So in this case, our trace verifier memory will be also containing signature related to this program. And this signature also will be extracted from the binary static analysis or computed before uploading the program to the RISC-V core. So we present an example of working in the code and control flow integrity mode, where we will verify the code integrity of the program that will be executed. So I took these examples that we shown in the previous slide. So at the address 22C, in addition to the destination address, there will be a signature of the basic block just executed. And we can see that at the branch instructions, there will be also a packet that will be sent containing the signature of the basic block 1. And the same thing for the return instruction at the address 390. So with this approach, in addition to verifying the signature, the verification latency will be reduced because the packet is sent after each discontinuity instruction. It will be more precise because after, for instance, executing the instruction 380, we can know the reported address after the branch to check if it's taken or not. So from here, we arrived to the results. So we implemented both approaches, the one following the trace encoder standard and the second one enhancing it as an FPGA implementation using on a IBEX RISC-V core. And we did so, we simulated fault injection attack and experimental electromagnetic field attacks on it. Our programs that have been used were compiled using the RFE32 IMC instruction set architecture. So we present to you the cartography of the IBEX connected to the ROM and to trace encoder and trace verifier with some faults that have been detected on the RISC-V core or trace encoder. From our simulations and experimental setup, I put in a small table the covered threads that you can see. So the TV is a solution that followed the trace encoder standard, which with it we can detect skip on function calls, and also we can detect if the return address has been changed after calling a function. And we can see with the other solutions enhancing the trend standard, TV4CFI, CCFI, CFEI, we can detect more threats depending on the granularity of our protection. And we can see that with this enhancement, the verification latency will be reduced because the packet is sent after each discontinuity instruction compared to the one following the norm. So here in this presentation, I described approaches for verifying the CFI of a program. The first one is following the trace encoder standard, and the second one, why enhancing the standard in order to cover more complex faults and also to cover faults on the microarchitecture of a RISC-V core. For both approaches, we don't have software overhead as our implementation does not modify the user code, neither the RISC-V compiler, so the metadata that are generated are by a custom program independent of the RISC-V compiler, and they are stored in a standalone memory connected to the trace verifier. From this work, also we look forward in order to check how we can treat indirect calls for forward edge attacks, and also to enable the branch prediction, which is compatible also with the trace encoder, and at the end, to upgrade our solution to handle interruption and core exceptions. From here, I arrive to the end. Thank you for your attention. I'm looking to answer your questions. If you have time for questions.
Now we have time for questions. We've been quite fast. Are there any questions? Questions? Yeah? No. Please?
Okay, I will not shout. Okay, so my question is, I understand the verification aspect. Are you considering eventually wiring this somehow back so perhaps this could be used by the system itself to detect faults? Not another observer, but perhaps reporting some kind of verification fault back to the OS or something like that.
I did not listen really.
I mean, I realize the overhead and how slow that would be, but again,
Yeah, so we are speaking about the overhead, about the solution, if I correctly listened to heard the question.
Hello?
Yeah, now I can hear you.
Okay, you're monitoring with another host today. The result of the verifier, where does that go today? That goes to another core?
Okay, so till now we are just notifying the developer of that the attack has been made or not. So the alert, if you can see here, the alert signal, or we cannot see, the alert signal for now is just to tell us if the attack has been made or not, but it could be, for the future work, it could be related to another core in order to take action to stop maybe the program or to take other action correcting the execution of the program.
Could this be used for like a lockstep solution to detect faults?
So the detection, yeah, it could be made software by software or hardware, but yeah, it will be, we need to discuss it, but yeah.
Thank you.
You're welcome.
From the use case, do you mainly have fault detection or also security in mind?
So now I show an example comparing two pins. So we did our experiment and also the electromagnetic field attacks on the IBAX core using the verify pin use case. And we tried to bypassed actually the verification. And for the simulation, I used benchmarks from Pulpino platform, from mbench IoT, and some classic ones like the memcompare and memcopy codes.
At the higher level, is that more for the assuring that the system is safe, or is it also, I mean, CFI is often be used for classical attacker detection and monitoring. Are you also going into that direction?
I guess yes, because it's, how to say, we need to verify that the program was correctly executed, so that's why we need to check the program behavior and where the program has gone, so that's why we will use the CFI verification solution. So for this, our aspect, it's a co-design solution, so we have a small of the software part and more in the hardware part. And so our experiments, we did injection attack on the RISC-V core on it, and we tested, and it's correct. So we detected attacks, so I guess yes.
Okay, thank you. Sorry to stop here, but